essentially for machine vision, and as you may think about it, it has a lot of applications in the field of robotics, and especially in mobile robots. So, first of all, I would like to ask you, have you ever seen a rabbit? Do you know what rabbit is?
Yeah.
Yeah, of course. Well, little fluffy thing.
Yeah. Very delicious.
Okay. It depends on the taste, but still. An interesting fact about them. They sleep with open eyes. Do you know the reason about it?
Using their eyes as cameras?
Well,
Sensors.
Okay, we all use our eyes
No,
as sensors.
their mind is sleeping, but
Yeah, but what's the reason?
They are scared not to be eaten while sleeping.
So the skin. Okay, do someone?
To feel any danger around.
Well,
Or it's not true.
yeah, it's true.
They can't cause them eyes.
They can't. Their skin is short, and if they close their eyes, their butt opens. So, okay. So you see how important is the vision for the mammals and for the creatures overall, in general. So, you may think the same about machines. The machine, as Mr. Chuvakov said, is stupid. It doesn't know, it doesn't realize what the machine is doing. And if it doesn't have sensors, vision, algorithms for machine vision or something, it cannot understand where it is going. I mean, for example, if you have a robot arm, industrial manipulator, for example, there are a lot of them: welding, painting, putting things from a conveyor to a storage or whatever. And in that matter, they are doing actions, motion. And you may imagine the motion of the robot car, right? The programmer told that robot to do a particular motion, but the robot itself doesn't have senses. He doesn't see, he doesn't sense the environment. That is why it's so dangerous to be around such industrial robots, because as Chuvakov said, it may hit you in the head, so it hurts, you may die also. So it's dangerous, they are placed in cells. Well, vision is important for robotics. For the robot to recognize things, to know where it is, to know the environment. As specialists who are involved in creating of robots, you know how hard it is to estimate the position of the robot, correct position, right? Okay. So machine vision is one approach in that direction. It gives the possibility the ability, actually, it gives the ability to the robot to sense its environment. Okay, so the outline of my lecture is as follows. First of all, I will try to point your attention to pattern matching, then to object tracking, object following, and some applications like traffic lights recognition and robot football. All of this research is done according to our projects, so they are familiar to the majority of you. And probably it won't be anything new as a topic, but I think I will be able to present you some new knowledge in that direction, which may be useful for you after that in the future. Well, first of all, pattern matching. This task is given to the babies, to the small children. You know? Is it right? Yeah, of course. So, toys like this one, the shown on the screen, are given to as presents for the small children. And like the children, there are a lot of similarities between the robot and the small children. The small child. The child learns through trying. He tries something, and then by experience, it knows whether the result will be good or bad or something. So, speaking about artificial intelligence and the machine vision is an area of the artificial intelligence. We cannot go without pattern matching. So, this is the answer to what is pattern matching. And now we are going to see how we are doing that. Well, we are in the technical university, so we cannot go without some equations. Actually, it's not that hard to understand them, but it's scary when you see them for the first time. It's called cross correlation. Have two, let's say, signals. And we have 2D cross correlation. Why? Because an image is represented as a 2D matrix, right? If you put an image in MATLAB, are you familiar with MATLAB? No, it's a joke. Of course you are familiar. Everyone knows MATLAB nowadays, at least in our university. Okay, if you put an image in MATLAB, it's represented as a 2D matrix containing all the values of the different pixels of the image according to its color and position. Okay, so here is such a matrix. And to estimate the cross correlation between a target and this matrix here, we have to calculate this formula, which seems pretty big and frightening and so on, right? It's scary, I know. But relax, it's not that bad at all. Actually, you have to take all the numbers and multiply them and then to sum everything together. I mean, we take this number in the image and we multiply it by this number here in the target image. Then we take the next number, multiply it by this one. The next, and all the results are come together and form one single value, which is the value of the cross correlation function in that particular point. That's all. So, what that means in practice? We have an image and a target. They are represented, actually they consist of many points. And our goal is to have a better camera with better lenses, with better CCD and so on, to have many points, to have a better resolution, right? But better resolution means many points. So the greater the number of points, the slower it will be done. So this algorithm requires a lot of time to process. Okay, but let's return to the basics of this algorithm. So we cannot show, we are not able to show every number for this image because there are a lot of pixels, but we can see the whole image. So this is our target, and this is the image in which we are looking for that particular target, right? Okay, so now we have to do these calculations for every single point in that image, as shown before, and we are going to have a function. I mean, all those numbers in a 3D plot. If we put them in a 3D plot, there will be some kind of surface. And in the point where the image, the part of the image, matches directly, or I should say closely, the target image, there this function will have a maximum. So this is the approach. We are calculating the 2D cross correlation function, and we are looking for a maximum. Simple enough, right? Simple enough. Okay. Object tracking. Of course, cats are famous with their calculations for object tracking. And as every decent scientist, I conduct the experiments with myself. So I'm very glad that I'm not a physician, a cardio specialist or whatever to cut myself, but shooting, taking pictures of myself, it's not so painless, so painful, so it's not a big problem. So here is the target image. Here is a picture of me, actually in the hotel room in Slovenia where I conducted the experiments and wrote the article. So we have in MATLAB, everything is in MATLAB actually. We have a video input, and first of all, I have to resize the image of my camera. Why? Any ideas?
To match it with the pattern that you have from before.
Well, to shrink my head to be as big as my face?
No,
No.
to reduce the processing power needed to use the image.
Of
To
course,
simplify it.
because I have pretty nice notebook with well, HD camera and something like this. And when I take picture of myself, it makes a pretty huge file. I already spoke about that. And if the image is with high resolution, namely HD for example, the processing time will be several minutes. And I would like to, for this algorithm to work online, in real time. So I need to shrink, to resize the image, first of all. Then I have to make, to perform a color conversion. It depends on the color space which is returned by the camera. I need to work in RGB format, and if it returns a different format, I need to convert it. Then I perform 2D cross correlation of this image, of this stream, with the target image. Then find, I'm trying to find the maximum, and at that coordinates, I place a symbol, for example, X. Actually, crosshair, X, circle, whatever. I could use different symbols, but crosshair, and if I move my head, the crosshair follows me. Exactly in the same way, the cat on the previous slide did with the sniper. Okay, so those coordinates might be used by the navigation system of the robot to track the object, but I will speak about that after several slides. And as I told you, when I move my head, this little red X, I don't know if it is clearly visible from there, but there is a little red X on my nose. And it moves, it follows me. But if I turn my head slightly to the right, or if I step out or step in, my head gets bigger in the picture or smaller, and it just cannot find my face anymore. Because for this algorithm to work, you have to put a threshold and to look for a maximum, but not for the value of 1, because this is full similarity, and it can be achieved. Why? Because even if my head is not moving, the light changes. The conditions in the room are changing. And it just cannot be 1, the value of 1. So I put a threshold, for example 0.8, and above that threshold, the algorithm tells that it has found me, and below that threshold, it loses my face. So when I move my head, it falls below the threshold, and it loses little bit different approach, which consists of constantly updating the target image. So, the idea is simple. You're looking for someone in a crowd, for his face. It's someone you know, and you're looking, it's very crowded, and you find, oh, there he is. And when you see his face, you see his position, right? And even if it turns his head, and you see the back of his head, you know that he is on that position, and you start following that person, right? But not looking at his face anymore. So the idea is the same. The algorithm searches for something familiar, for example, my face. And when it finds me, it starts constantly updating the target image with the area in the image in that position. So even if I start turning my head, it will slowly actually constantly update it, and eventually it will have the back of my head, for example. If I'm moving with a speed less than the speed of processing, obviously. Because otherwise, if I turn my head very fast, it will, I will get lost from the image. Okay, so that's what this new target means. It pulls from every frame on that position every new target. But it should find the target at least once. Okay, and as you see, with that approach, even if I turn my head to the side or like this, or even if I step out or step in, the algorithm still works. So it's pretty scary. Why? It could be used for guiding a missile. And once it locks the target should move very rapidly to the side or whatever to get away from it. So it's based on that idea. Okay, so you may see the results represented graphically. With the constant update, it stays quite close to 1. Why? Because it matches every time the same image, very close to the image. And with the traditional approach, if I turn my head, this is slowly turning, this is fast, rapid turning. And with the traditional approach, it falls below the threshold even. At that point, the algorithm I will be lost from that. And with my approach, it will stay close to 1, 0.9, something like this. And if I turn my head fast, you will see that I will get away from it, get lost in the picture anyway. So for need what? More processing power to do faster processing. And also more what?
Frame rate.
Yeah, frames per second. Faster camera, faster processor. Okay. And then there is no escape. Once it locks you on the screen, it's over. Okay, object following. Again, it's very important. Do I need to speak why object following is important? I think it's obvious from the picture on the screen. Okay. We are constantly following objects in our life. And I'm not speaking just about girls in my case, because I still think I'm a man. So, we are following girls, cars, whatever. And in the nature, it's crucial for survival. Okay? The same is for the robots. Probably you're familiar with our Robotino robot, mobile robot platform made by Festo. Actually, this is the moment I would use for introducing the project we won this year, and as part of that project, for example, the middle or the end of the spring, we are expecting fully robotized factory, our product factory by Festo, and there in that factory, all the service for the station, for the stations will be done by robots, which are the same like Robotino. Actually, they are Robotinos, but equipped with forklifts. So it will be able, the robot will be able to lift things and place them somewhere. Okay? And now, if you allow me, I will continue with this approach, this idea. The problem definition is as follows. We have a ball, and we need to follow. Simple enough, right? Simply for a human. Not so simple for the robot. But I will show you how, using the previous approach with 2D cross correlation, it will be done pretty easy. I have to estimate the position of the ball and to calculate the errors. And because this is 2D, two-dimensional space, I need to calculate the error along the x-axis and the y-axis. So, first of all, I need to perform primary image processing. This is necessary because of the fact I mentioned earlier. I mean, the light changes, the condition changes, and to maintain them relatively the same, I need to perform this primary processing. So, first of all, I calculate new color coordinates. And you may see the result. This is the picture, and this is after normalizing. This is called normalization of the color coordinates. And after normalizing the coordinates, I end up with such picture. You may notice that it is the details are not so obvious, but the goal, our target, the ball, is probably more clearly seen. So it depends less on the surrounding white. And after that, I take only the red channel because I have cover camera installed on that robot, and I need only the red channel. Why?
Because the ball is red.
Yeah. The ball is actually orange, but the red
Is in this picture.
dominates income. So that is why if I have a girl with red skirt present in the scene, the robot will forget about the ball and starts chasing her. Actually, we do the same as humans, right? Okay. So, again, I took the ball out of the picture once, and I used that as a target. So, the same principle, the same idea as previous, pattern matching. But this time with some pre-processing. And I end up with many red points. Okay, I have to explain that. So, I'm looking in the picture for two things. First of all, I'm looking for dominating red color. And second, for the target. Why? Bless you.
Thank you.
Why? If I'm looking only for red color, I will see on also the red skirt of the girl. And actually, in our case, the red fire extinguisher in the mechatronics one. And if I'm looking only for the shape to match the pattern, it will more time will be needed for processing. So first of all, I'm looking for red dots, and at that spots where I find red dots, I'm performing the pattern matching. So this approach makes the algorithm work faster, because I'm processing not the entire image, but only those spots where I have some red dots already found. Okay, so at first it seems more difficult, but in practice it works faster. Okay, and I end up with the coordinates. Oh, sorry, probably. Well, I end up with the coordinates of the ball, and from then, from this point on, I need to calculate the errors and to construct a PIT algorithm for controlling the position of the robot according to the errors. Okay, and I have to show you some videos, but let's talk first about the algorithms, and then you will see the results. Okay, now again the same approach, but for traffic lights and traffic lights recognition. And again, I'm not looking at the color, red or green, white. Know the reason why I'm not performing the image processing by color and by shape, but the shape white. Any idea? What color is the one? For example, you have a green one. You turn it on and you take a shot with the camera. What color is the one?
It's not good.
Green.
It's not good.
And what color?
White.
White. Yeah. Big white dot. And if the lamp is red, again white.
White, yes.
So we have specialists in photography. So what's the correct term to use? The image is overexposed or burned. Yeah, overexposed or burned. We deal with that problem a lot. So we cannot look for red or green dots in that case. So I decided to look for shapes. And if the left lamp is lit, no matter what color it is, I told the system to decide that this light is red. I mean the signal, the traffic signal is red. And if this is the shape, the right lamp is lit, then it assumes that the green signal is turned. And after that is the same algorithm. Absolutely the same, like the one I already spoke about. And this is the flow chart for the system, for the algorithm, for the control system. And eventually, as you will see on the video, it will recognize correctly the traffic lights. And at the end, I would like to speak about robot football, robot soccer. We are in Europe, so robot football. And this is the idea. We have a robot on the field, and we need to estimate its position. We know the position of the ball, and we need to estimate also the position of the ball. So we acquire the image, then we perform color separation, some clustering. And what clustering means? This is to find the coordinates of all points, pixels in the image, which have particular color. because they form clusters. If you take a shot, take a picture of a red ball, and if you start working through the image for red dots, it will form a cluster spot. Okay? So, the clustering is performed like shown here for the red, green and blue component of the image. Why red, blue and green?
RGB, this is the color pattern.
Please repeat.
Because of the RGB, this is the color patterning which you used in
Color
MATLAB.
space. Okay, that is why I'm targeting RGB images in my studies. Okay, so this is the symbol for a little bit of help here. Union. Okay, thank you. To unite two regions, so I'm separating the red region, the green region, the blue region, and then I'm uniting them in one region. And I'm finding their centers with these algorithms. And the center of the red region will be the center of the ball, because our ball is red, or at least it's the dominant color in the ball. The center of the green blob or spot or cluster is the one of the coordinates of the robot, and the blue is the other. I will explain that. So this is the green blob, and this one here is the blue. And if we have coordinates of that point and that point, then we can connect them, and we could calculate those angles alpha and beta. Actually, the orientation of the robot and the position of the ball according to the target, because we know in advance the position of the target. And after that, when we have calculated those angles and positions, we may construct the strategy for achieving those positions. I mean the movement of the robot towards the ball. For example, if this is the start position and this is the position of the ball, first it may rotate, then drive, then rotate again. So this is turn, drive, turn strategy. And it depends on what the strategy we choose. We have to choose.
The other
What?
footballs.
Ball position.
The ball position?
No,
In other robots.
Ball positions.
Yeah.
Okay. And
Kazakh.
what else?
Go where the target is.
Okay. Position means where it is. But what else? Okay. I will give you an example. Using turn, drive, turn strategy, I need to
Face the robot to the goal.
go there, facing the subwoofer. So, turn, go, drive, turn. And may I do this one? In what case able to make that one, that movement, that strategy. If the construction of my robot allows that. So, for example, Robotino has omnidrive. It can turn and drive simultaneously. So, if you use two-wheel robot, you need first to rotate, then to drive, then to rotate to position, to angle, to the desired angle. And if you have omnidrive like in Robotino, you may start turning and moving in the same time. Okay? So it depends on the construction of the robot. And
Scopchanov, може ли
Да.
са малко да застанете да ви направя една хубава снимка без да въртате?
така ли?
Защото там е водата хваща.
Добре.
Не,
Как наказвам?
да си.
Добре. Друг да иска да се снимаме?
После.
Actually, those pictures were taken with the equations on the background, which puts me in an unwanted light. I mean, usually I'm not dealing with a lot of mathematics, but more practical things. Okay, so those are the equations to calculate both angles. Okay, and this is the process from taking the picture, segmentation, finding the centers, which are not visible here, but there are white crosses in the centers, interconnecting all the dots and calculating all the different angles. Okay, and I would like to show some results in form of videos. For example, for ball following is the first one. Okay. My iPhone turns upside down the. Ще го направиш ли, ако обичаш? Извинявай, че ти говоря на български.
Само кажи колко е полетиш, защото трябва да пусна да гледам.
Добре, Бълфол. Размери положение на карта.
Видео да ще...
Огледално.
Гледално.
Обръщам. И огледално също. Добре, пусни го от YouTube. Там ги има качени всички. Да. YouTube наклонна черта Scopchanov.
Други вариант ние си да натим долу.
Да, може.
Това ще е по-лесно, май.
С сисата this is the visualization in MATLAB. And any idea what we think? What do you think we need for precise tracking?
One core
One?
core
Okay, let's watch the next video and then we are going to discuss that. But you already know that if we switch the position of the whites, red and green, we will stop on green and start on red, because it doesn't detect color but
The
shape,
position.
position. Okay, and this is one video which is not connected with machine vision, but it's fun to watch because it represents fuzzy logic control for robot, you know. Actually, that's the subject of the lecture of Alex Tormashi from Hungary on Thursday. So I will try to invite you all. And you may watch this video, and then we are going to discuss the problem I presented to you. It roams randomly, but it doesn't hit the walls. That is the goal. And the interesting part is that it's controlled not by hard logic, but conventional logic, I should say. But fuzzy logic. And you can also see that it uses the same strategy to turn while driving. So this is possible because of the OmniDrive. Okay, so my question was, as you saw, there is an error in the tracking process. So it doesn't follow the ball perfectly. What do we need to follow the ball perfectly? I mean, if this is the center of the robot, of the camera of the robot, and this is as represented there, the position of the ball, to match them perfectly every time. What do we do?
moving camera.
Moving what?
Camera. Tracking camera.
Yes,
Which
but
will be
the camera.
independent from the robot. It will track the target, and the robot will be moving simultaneously.
Yeah, but I need for the robot to follow perfectly the movements of the ball.
Faster camera and image processor.
As the correct.
Faster?
It is.
Faster?
Camera and image processing unit.
Okay, this may be true, but
Faster robot.
faster robot, because if you try to track the position of a rabbit with a snail, you will fail, right? Because the snail is not fast enough. It may see the rabbit, but it won't be able to follow it, right? So you need a faster robot which is able to react quicker, to react rapidly for the changes. Okay, so but this reaction is connected with a lot of stress for the motors. Actually, this is topics which are covered by Professor Marinov in his lectures. So I will try to invite you in his lectures. Please. Okay. I started with rabbits, and it turns out that I ended with rabbits. So I would like to thank you for your attention, and I will be glad to answer all your questions if you have any. Please. Yeah?
What was the tracking, the clustering algorithm described?
Well, first of all, you need to find all of the coordinates of the.
What's the name of the algorithm?
Well, I didn't find a particular name, just clustering. Not clustering of Scopchanov or something.
Because it looked like a machine learning algorithm called K-means clustering.
Yeah, K-means. Yeah, but this is for classification, and it is based on finding the closest neighbor, right?
Yes.
Yeah, it's similar, but here I'm looking for particular color. So, and when I find all the dots with all the pixels with that particular color, I'm finding the center. Yeah, it has a lot of similarities to the K-means, but it's not exactly the K-means.
Yeah.
But you're on the right track. Just probably a different application of K-means. To be honest, I didn't think, I haven't think about it. But it has a lot of similarities to the K-means, yeah. And any other questions? Okay, if there are not.
I want to ask.
Please.
Okay, during the whole presentation, I didn't hear anything about the shadow tracking, and I think the shadows are one of the objects that are the most easy to be tracked by a robot. Like if you have a static source of light in some room, and you give a task to the robot to follow some object, and you have this basic information, if the robot can detect the shadow of the object, you can always determine where is his position in the room or in the place, basically only of the shadow of its form, its density, and etc. So I think it's like an important tracking tool.
Yeah, it is.
And you didn't mention anything about that, only about coordinates and how to follow it with the dots. Why is that?
Okay, I will explain. First of all, as you saw, I presented materials which are connected with my studies and with our projects.
Yes, okay.
And in my studies, I deal mainly, when it goes about image processing and object recognition, I deal mainly with cross-correlation. Well, it turns out like this. Yeah. And second, I just would like to discuss a little bit your idea. Of course, it is correct, but it needs first a static source and absence of any other light source. So for example, in this room, you are not able to use that algorithm because there are windows and there is light coming from them. Заповядайте.
That means if you have two or more source of light, that means the object will have cast 2 or 3 shadows.
Yeah,
And
but this one is changing. And it will be difficult to calculate because you need one I'm thinking about now and you need something to determine the position of the sun in order to know at what angle are the shadows cast, and then to compare with the actual angle on which the robot sees them. Right?
yes.
So it requires a lot of changes to the environment, and my algorithms, actually they are not mine, but I'm presenting them, are based on the idea that no changes are introduced to the environment. For example, you may use beacons, radio beacons, light beacons, ultrasonic beacons, whatever, to navigate the robot. But this needs modification of the environment. So you need to place the sensor, the beacon here at that particular position, and you know the position. And I'm trying to make it independent of the environment. Furthermore, as you saw, I'm trying to minimize the changes, to minimize the impact of the changes in the ambient light.
Okay.
So my goal is to make the things work independently of the environment. If you place them here, they will work, hopefully. If you place them in any other room, it will work. And for example, I would like to explain a little bit in that direction. Many algorithms work only in predefined conditions. For example, there are visual inspection systems. For example, you produce bottles, like this one, and you need to check it for any defects. And the visual inspection system, some of them, uses algorithm which requires for the bottle to enter a dark space, and then to take a picture in those predefined conditions, and then to be processed. So my goal is to make it in the non-dependent
from the environment.
Any circumstances.
Yeah.
Okay, thank you for the answer.
Thank you for the question. And any other questions? But anyway, the idea is very good, and I would like to suggest to the no, just to finish, please. To suggest to the members of the robotic and mechatronics club to try. No, I'm serious. It's a really interesting idea, and it may come something out of it. Okay, so next question, please.
So after the colleague said that tracking the shadows can be useful, I I have remembered that the technology of the optical mouse is more similar with this. There is a lighting source and there is a camera which counts and track the shadows which are made from the surface where the mouse is. So this is maybe some kind of answer or some kind of technology which can be used from the robot to track the way they are moving to reduce the error of the slipping the wheels and etc. So this with the shadow thing with the cameras is very useful.
Okay, if I may add something, it's not an answer because you didn't ask a question
Yeah,
actually, but I will explain a little bit in that direction. And for my PhD thesis, I did some review, let's say, of articles, and in my studies, I realized that there are two ways for navigation. I mean active and passive. Active is the same as I told you. For example, you put beacons, it's active. It actively transmits signals which you intercept, and knowing where the beacon is, you estimate your position. For example, the satellites work like this. You have satellites at particular positions, and if you intercept the signals from them, you estimate, depending on how fast the signal comes to you, you estimate your position. And the other one is passive. The first one was active, and the second one is passive. Nothing emits nothing. I mean, there is no active emission. For example, you do you know how you are able to see me, for example? Sorry?
No, not.
Why? The correct question is, why are you able to
Because
see
you
me?
emit the light from the sun.
Yeah, but I don't emit. I reflect the light from the light source. If I was radioactive, for example, I would be able to emit light, but I'm not emitting anything.
Actually, the human body emits light, but it's too small for our eyes. Our eyes are too weak to see it. But some animals can see us how we sparkle.
Probably that's interesting. I will try to read about this. But okay, mostly we reflect light, right?
Yes, mostly yes.
So the same idea is there is signal, but it's not actively emitted. It's reflected. Okay. So passive navigation and active navigation. The first one requires beacons, or in your case, it may not be a specially placed beacon. Well, it is actually, because if you put a light source, it serves light beacon. If you look for shadows on the ground, for example, because the moving platform is closer to the ground, for example.
This option it can be used in three-dimensional system because if you lift the object in the air and make it in the third dimension, the shadow will change again its size. So you can actually track it everywhere, not only on the floor.
Okay, so, but that's correct. But my idea was to to show that this is some way of active
Yes,
type.
yes, yes.
And I focus my studies on passive type. So that is why I'm only taking pictures, but not emitting. For example, you may emit ultrasound and wait for the
Right.
reflection, yeah, and measure the time of flight, etc. But I focus my studies on passive radiation. Okay, if you have any other questions, please, I will be glad to answer, if I can, of course. Okay, then thank you very much for coming, and I would like to invite you to the tomorrow's lecture will be which will be in 2 o'clock p.m. and the place is the same, and I will be glad if you come here. Actually, tomorrow we are going to listen a lecturer from Ukraine. It will be an online lecture. We're going to see him on the screen. And the colleague is from Sevastopol, Ukraine, and he's going to speak about modeling and tracking of mobile robots. Actually, this is the subject of his work, so he's a specialist, and I think it will be interesting to listen to him. So thank you very much again. And